So in this video, we're going to look at arrays as a data structure. So the most important thing to understand about arrays is how they're stored in memory. And essentially, they're stored as one contiguous block in memory. And what I mean by that is you don't have the items or elements in an array scattered throughout memory. All of the elements, items, whatever you want to call them, in an array, they're all stored as one contiguous block. So let's say an array starts at memory address 100. That's a bogus memory address. You wouldn't have a memory address like that, but to keep things simple, let's pretend that we have an array that starts at memory address 100. And let's say that array is 200 bytes long. Well then, what happens is, starting at memory address 100, the following 200 bytes are the contents of the array. So the array is just one huge block, and that's why we have to specify the length of the array when we create the array, because that tells the JVM how much memory it has to allocate for that array. And it's one reason why arrays can't be resized, because if they could be resized, then there'd be no guarantee after that whatever, when we added extra space on, that extra space would be in that same contiguous block of memory. So arrays have a static length, and when you create an array, there's one huge block of memory allocated for that array. So the elements of an array are not scattered all over the place in memory. Now, the second important thing about arrays is every element in the array occupies the same amount of space in memory. For example, when we created our int array, every item that we put into that array will be an integer. And in Java, an integer is 4 bytes, so every value in our int array was occupying 4 bytes in memory. You can't have an array element that occupies 4 bytes, and then the second array element occupies 12 bytes, and the third array element occupies 300 bytes. That doesn't work. Now, at this point, you might be thinking about objects and thinking, well, wait a minute, what if I create an array of strings? I mean, the strings in the array could be of different lengths, so they're going to be taking up different amounts of memory. What's important to understand when you're working with objects, not primitives, like when you're working with ints, but when you're working with objects, what's stored in the variables is an object reference. So when you create an array of objects, what's stored in the array elements is a reference to those objects. And object references are always the same size regardless of the type of object they're referring to. So if you create an array of string, what you're actually storing in the array is a bunch of object references to the string instances. And those object references are all going to be the same size. And that's why you can have an object array and store any type of object in there. It's because the object references to the different instances are always the same size. So arrays occupy one contiguous block in memory, and every element in the array occupies the same amount of space in memory. So because of that, we can easily calculate the memory address of an array element based on its index. So if an array starts at memory address X, and the size of each element in the array is y, then we can calculate the memory address of the ith element, so array I, by using the following expression, x plus I times y, and we're going to look at an example of this in a couple of slides, so you'll see an illustration of this. So basically what that means is if we know the index of an element in the array, then the time or the number of steps we have to do to retrieve the element will be the same no matter where it is in the array. Because all we have to do to get the memory address of that element is x plus I times y. And that works whether we want the first element in the array, or the 5,000th element in the array, or the 1,000,000th element in the array. All we ever have to do to get really quickly to that element is do that simple calculation to get the memory address. And this is made possible because of the first 2 points, because arrays are one large contiguous block in memory, and because every element in the array occupies the same amount of space in memory. So let's have a look at this for the array we just created. So we created an array of length 7, so the valid indices are 0 to 6, and the values are 20, 35, minus 15, 7, 55, 1, and minus 22. Now, for this example, we're going to pretend the start address of the array is 12. As I said, that's a bogus memory address. It doesn't matter what the number is. And because these are integers, the element size is 4 bytes. So if we wanted to get the element at array 0, well, that's equal to the start address of the array, right? Because the array starts here at 12, And so the first element of the array is actually going to have the same address as the beginning of the array. So if we want the address of array 0, we get 12. If we want the 35, we need to jump past the 20. And so if we want array 1, we're going to start at 12, and then we're going to add 4 bytes, because we know that the size of each of these elements is 4 bytes. And so if we want the second element in the array, we start at the memory address, which is 12, and we add 4 bytes. And now we're at the start address for the 35. So that's 12 plus 1 times 4 equals 16. And if we go back to our calculation here, that's the x plus I times y. So x is the 12, I is the index, which in this case is 1, and y is the size of each element in the array, which is 4. So that's how we're doing this calculation. So if we want minus 15, we've got to jump over 2 elements. So we're going to start at 12, and this time we're going to add 2 times 4 to it to get 20. So the 15 will start at 20. If we want to get to the 7, we've got to jump over 3 elements to get to the 7. So that's going to be 12 plus 3 times 4, and that'll give us 24, and so on. And this is possible because the array is one contiguous block in memory, so all the elements are stored in one block in order, and also because every element occupies the same space in memory. If that wasn't true, if either of those two requirements weren't true, we would not be able to use this simple formula to quickly go to an element in the array. So what this means is that if we know the index of an element in the array, we can get to it really quickly, and it doesn't matter where it is in the array. I mean, if you look at array 1 versus array 6, we're doing the same calculation. And we're actually doing the calculation here as well. I didn't show it, but this is actually 12 plus 0 times 4, which is 12 plus 0, which is 12. And now maybe you can understand why array indices are 0-based. Because if they weren't 0-based, if they started at 1, we'd have to subtract 1 here, because then we'd have 12 plus 1 times 4. That would be wrong, because then we'd get 16 for the first one, so we'd have to always subtract 1 before we did the multiplication. Starting the indices at 0 means we don't have to do that. So we can just substitute the array index in here. Because remember, this is 0 times 4. I probably should have written that out, but I didn't. So one of the things that arrays are really good at doing is retrieving elements if you know the index. So if we know the index of the element we want, we can get to that element very quickly, regardless of where the element is in the array. Okay, so now we understand how arrays are stored under the covers, and we understand why when we have an index of an array, we can get to the element really, really quickly. Doesn't matter where the element is in the array, we do the same calculation. So with that in mind, let's move on and look at the big O values for array operations. Okay, so we've learned that arrays are very efficient when it comes to retrieving elements. They're also memory efficient because we don't have to store any extra information with each element in the array. You'll see later on that with many of the other data structures, we can't just store the value, we have to store extra information with the value, but that's not true for arrays. So arrays are efficient when you know the index of the value you want to retrieve, and they're also memory efficient. So let's quickly review here. To retrieve an element from an array, when we have its index, we multiply the size of the element by its index. And remember, every element in the array will have the same size. And multiplying the size of the element by its index gives us the offset from the beginning of the array. And then, of course, we need the start address of the array, and we add the start address to the offset of the element, and boom, we have the memory address of the element. So once again, to get into array 0, if we're starting at address 12, assuming that's our array start address, that would be 12 plus 0 times 4, which is 12. To get 1 would be 12 plus 1 times 4 to get 16, etc. So it doesn't matter how many elements we have in the array. If we have one element in the array, it's going to take us 3 steps to retrieve the element, right? These 3 steps here. Any element in the array. If we have 1,000 elements in the array and we have an index of an element, 3 steps. If we have 100,000 elements in the array and we want to retrieve an element, 3 steps. 1,000,000 elements, 3 steps. 1,000,000,000 elements, 3 steps. And so, as you can see, unlike our adding sugar to your tea example, the number of steps does not change. as the number of items changes. So if the number of elements is equal to n, the steps to retrieve never changes. And when we have this situation, we have what's known as constant time complexity, and that's designated by O of 1. And so our adding sugar to tea algorithm had a linear time complexity, which was O of n, because n influenced how many steps were required in a linear fashion. But here, when it comes to retrieving an element from an array, when you have an array index, the number of items in the array has absolutely no effect on the number of steps. The number of steps is always going to be constant. And so this has a constant time complexity, which is O of 1. It means that as the number of items increases, the algorithm doesn't degrade at all. So when it comes to retrieval, one of the advantages of arrays is that retrieving an element, when you have its index, can be done in O of 1 time, which is the best you can get. And so that's one of the advantages of arrays. So let's take a look at some of the disadvantages of arrays. So let's go back to the IDE. So we have our array here, and let's say we read these numbers in from a file or from a database or something. So we don't see this. I mean, this could be anything. And then we have maybe an interface where we let a user type in search values, and let's say the user types something in, and because of what they typed in, we want to retrieve the number 7 from the array. Now remember, you don't have this information. We're pretending we read values in from a file. We have no idea where integers were added into the array. So somebody comes along now and says, get me number 7 from the array, but I don't know what the index is. So all of a sudden, we can't just go right to the position in the array because we don't know the index for number 7. So what do we have to do? Well, we're going to have to do something like this. I'll change our code here, and instead of printing out, we're going to say if int array I equals 7, then we're done. So I'll say break, but what I'll do here is just say int index equals -1. And then when we find the 7, we'll say index equals I, because that's where the index for 7. And then after the loop, we'll print the index. Let me make some room here. So we're expecting, of course, 3 to be returned, so let's run. And indeed, the index that's returned is 3. But we couldn't just jump to 7 because we had no idea where 7 was in the array. So when we've been talking about retrievals, we've been talking about retrievals when we know what the index is. In this case, we didn't know what the index is. Somebody came along, they didn't say, give me the element at index 3. Instead, they said, give me 7. And that's all they said. Give me the value 7. Get that from the array. And we're like, well, we don't know where it is. So we had to search for it. And so remember, for big O notation, we always consider the worst case. So what would be the worst case for this? Well, the worst case would be that 7 was in the last position in the array. And so the worst case is that we had to search the entire array before we found 7. Now there are 7 items in the array, so n equals 7 for this example, and that means we would have had to have looped n times. And so in this situation, the number of elements does influence how many steps we're going to have to perform. Because if we have 100 items in the array, then in the worst case, we're going to have to loop 100 times. If we have 1,000 items in the array, in the worst case, we're going to have to loop 1,000 times. If we have 1,000,000 items in the array, worst case, 1,000,000 times. So this looks like linear time complexity, right? Because when n is 1, we have to loop once. When n is 10, we have to loop 10 times. When n is 1,000, we have to loop 1,000 times. So it's progressing in a linear manner. And so retrieval, when we know the index, we can do that in O of 1 time. But retrieval, when we do not know the index, the O value for that is O of n, because we have to find the item first, and in the worst case, we'd have to loop over the entire array. So let's go back now to the slides so we can talk about the time complexity for some of the other array operations. Okay, we know that retrieving with an index, we went through this, is constant time. Now we just talked about retrieving an element when we don't know its index. That means we have to search the array, and in the worst case, we have to search the entire array So the time complexity is linear time. That's similar to the situation we had with putting sugars in the tea. The number of steps increases in a linear fashion as n increases. So let's think about adding an element to a full array. So with our int array, it was already full. So if we came along and for some reason we wanted to add an 8th integer, we can't add it into the array because the array is full. We've learned arrays are not a dynamic data structure. Their length is fixed. So the only way that we could add an integer, another integer, into an array is if we created a brand new array that had a length large enough to take the existing integers and the new integer. So what we'd have to do is create a brand new array and then copy the integers over. And so this would also take linear time because creating the array doesn't depend on the number of elements, and adding the new integer doesn't depend on the number of elements. We just have to know where in the array to add it, so we'd have the index for that. But we have to copy all the existing elements into the new array, which means we're going to have to loop over the entire array. So once again, this is O of n, linear time. Now, if we want to add an element to the end of an array that has space in it, and assuming we know the index of where to add the element, well, that's going to be O to the 1, because that's similar to retrieving an element. When we have the index, we can figure out the memory address of where the new element is going to go just by using our simple calculation, and so that's also constant time. And the same thing if we want to insert or update an element at a specific index. We can do that in constant time because if we have the index, we can jump right to the memory location. Now, if we want to delete an element, and we're going to delete it by just setting it to null, or in the case of integers, 0 or -1 or something like that, we can also do that in constant time because all we have to do, if we have the index, is jump right to the memory location. Now, if we did not have the index, I don't have this on the chart, then it would take linear time because we'd have to search for the element first. So if somebody came along and said, delete the number 7 by setting it to -1, we'd have to search through the array first to find the number 7. Now, if we want to delete an element and we don't want to have nulls in our array or placeholders like -1, because that's basically dead space. So what we want to do is when we delete an item in the middle of an array, we want to shift all the other elements down. That's, in the worst case, that will be O of n, because in the worst case, we're going to want to delete the element right at the front of the array. And if we want to shift all the other elements down, we're going to have to loop over all the remaining elements and push them down. So that would be a linear time complexity. So essentially, if we have to loop over the array in any way in order to perform an operation, that's going to have a linear time complexity. If we don't have to loop over the array because we have an index, and so we can just calculate the memory address of the element we want to work on, then that's going to have a constant time complexity. So an easy way for arrays to remember the time complexity is if the code requires a loop, it's going to be linear time. If the code does not require a loop, then it's constant time. Now, I've gone through this fairly quickly because we're talking about arrays, and this isn't a beginner course, so I assume that you know what an array is and you would have some idea of how to code. For example, retrieving an array element when you don't have the index, or deleting an element when you don't have the index by, setting it to null, or adding an element to the end of an array that has space that you would know, that to write the code that keeps track of the last empty position, etc. So I'm not going to code those, and that's all I'm going to touch on for arrays because this really was meant to be a review, and I want to get into the sort algorithms. Now that we've looked at arrays and we have some idea of the time complexity for these different array operations, we can now get into sort algorithms, and we have a way of comparing how well a sort algorithm performs compared to another one. So I'll see you in the next video.